Hello everyone, welcome back to my channel. My name is Dr. Yogita Bish and today onwards I'm starting a new series called Electronic Configuration. In this series, I'm going to explain all the topic that you need to know to master this particular topic, which also includes some exceptions and the examples and principles. Alright, so we are starting with the first video of this series that is called as Quantum Number Guide. Here we are going to talk about all the quantum number that you need to know, N, L, ML, MS, everything. Alright, so let's just begin. So we'll start with what is quantum number actually and why do we need to remember this. Okay, so these quantum number you can just imagine these as your address. So when you tell your address to somebody, you tell okay you live in this country, in this particular state, in this sector, this is your house number, right? So 4 5 numbers are good enough to tell exact location of yours, right? So similarly these quantum number are the address of the electron of an atom. You can easily tell with the help of this quantum number what is the location of this particular electron in a particular atom. For example, oxygen, it has 8 electron, right? So if you need to know what is the exact location of the 6th electron of oxygen, you can easily tell if you know the quantum number of that. All right, so this is that important. Okay, so there are 4 quantum number as you can see: principal quantum number, azimuthal quantum number, magnetic quantum number, or and the electronic quantum number. Okay, so we'll start with number 1. Principal quantum number. This is represented by N, and this basically represent the energy level or distance of the electron from the nucleus. Okay, this also give you idea about the shells, which shell we are talking about. If you can recall the Bohr model, though this is not the exact representation of this, but there we had the nucleus surrounded by the energy levels, right? These shells. So this first quantum number N represent these shells. Okay, so first shell, second shell, third shell. So electron can be present in this shell, this shell, this shell, depending upon what is its quantum number, what is its principal quantum number. If N is 1, this represent 1, this represent 2, this represent 3. So if it is present in this shell, that means the principal quantum number is 3. And there is particular name for this as well. This is K. When N is 1, this is called as K shell. When N is 2, this is called as L. When N is 3, this is called as M. When N is 4, that is called as N. So N can have any positive integer value. N cannot have a zero value. It starts with 1, 2, 3, 4, so and so. 1, 2, 3, 4, any value. So this is K shell, L shell, M shell, N shell. Alright. Next is azimuthal quantum number. Azimuthal quantum number, which is also called as angular momentum quantum number. Okay, and this is represented as small l. Okay, and what does it represent? It represents the shape of the orbital. And what is an orbital? If you can recall, orbital is the area where the probability of finding electron is maximum. So this represents the shape of the orbital, and this also give you the value of the subshell. N give you the value for the shell, L represent the or give you the value for the subshell. Okay, and I'll give you an example. For example, if L is 0, that is called as S subshell. When L is 1, that is called as P subshell. When L is 2, that is called as D subshell. Okay, and when L is 3, that is called as F subshell. And they have a particular shape. When L is 0, that is when we are talking about the S subshell, it has this particular shape, spherical. I'm sorry, the drawing is not that good. Okay, and when L is 1, that represent the P subshell, and it has a particular shape which is being represented as this. Okay, similarly, if we have D subshell, that is being represented, this is S, this is P. D subshell is being represented as this. This is D subshell. Okay, similarly, F subshell, this is being represented this like this. Okay, this is F subshell. So as you can see, this particular quantum number, this represents the shape of the orbital. Okay, and what is the formula for this? The formula for this is L is given by 0, 1, 2, so and so till n minus 1. Okay, for example, if your principal quantum number for n is equals to, let's say, 3, L would be 0, 1 and 2. For, let's say, n is equals to 1, L would be only 0. For L is equals to 2, n is equals to 2, sorry, L would be 0 and 1. So with the help of n, you can easily find out the azimuthal or angular momentum quantum number. Alright, I hope this is clear. The third quantum number that we are going to talk about here is magnetic quantum number. Magnetic quantum number, which is being represented as M subscript L, ML. Alright, and this basically represent the orientation of the orbital in space relative to a magnetic field. Okay, so what is the orientation of the orbital? So to understand this, I'll give you an example. The P subshell that we studied earlier, right? It can have three particular magnetic quantum number. Okay, that is Px, Py and Pz. Okay, so the representation, as we have already studied, P orbital look like a dumbbell shape, but in space it can orient itself in x direction, y direction, or in z direction, right? So this Px, Py, Pz, these represent the same orientation. Okay, so when we are talking about the x, that means, let me just show you the representation. Okay, so if this is x direction, this is y direction, this is z direction, so Px would be like this. Okay, similarly this is Px. Similarly x, y, z. So py, if I have to represent py will be represented as this. Okay. Similarly, pz, if I have to draw, this is z direction, y direction and x direction. So pz will be represented like this. This is pz. Alright. So magnetic quantum number, it represents the orientation of the orbital. Now, how do we get to know that it has a three different orientation or three different orbital orientation here? So there is a formula for this, and the formula for this is given by minus L minus 1, 0 plus L minus 1 plus L. This is the formula for calculation of the magnetic quantum number. For example, when we have L as 0, then in that case ML would be just 0 if you put it in this formula. When L is 1, that is in case of S, this is S suborbital subshell, this is P subshell. In this case, ML would be minus 1, 0, plus 1 as per this formula. Okay. Similarly, for D, we have L is equals to 2, right? So, in that case, ML would be minus 2, minus 1, 0, plus 1, plus 2. Okay. So, in case of L, the ML has only one subdivision, that is, it is being represented by only this. This is S orbital. In case of P, the subshell is further divided into three subshells. So further three division. So this is represented as Px, Py and Pz. This is called as orbital degeneracy. Okay, so they all have the same energy. Similarly, d orbital, this is divided into 1, 2, 3, 4, 5. 5 parts, that is 5 space will be there, 5 degeneracy. There are specific term for this. For that you need to know the complex topic, so I don't want to go into this. So in a layman language, you can just understand this is further divided into 5 parts. So that is represented as dx, dy and so and so. Okay. So this was about the, not exactly dx dy, dx square minus y square. So that representation is different. For now, for today's topic, this is good enough to represent that this is further divided into 5, this is further divided into 3 and this is further divided into 1, depending upon the azimuthal, the magnetic quantum number. Alright. Then the fourth is spin quantum number. Spin quantum number, which is also called as electronic spin, and this is represented by ms. Okay. So what does this represent? Spin quantum number, it describes the spin of an electron. Spin of an electron. So basically this spin, it gives the electron a magnetic moment. Okay, and it can have only two values. The possible value for ms is either plus half or minus half. Okay, so to understand it properly, as I have already explained to you, that these subshells are further divided as per their magnetic quantum number, as S in 1, P in 3 and D in 5. Okay, now when we have to put the values here, like for S, let's say, so this is the subshell. Now I have to put the electrons. So the maximum number of electron which can come in each box here is 2, max 2 electrons. So when you fill this electron, these electron can have either upward direction or the downward direction. So the upward direction is considered as plus half spin, the downward direction is considered as minus half spin. They cannot assign towards the same direction. Okay, so there is a law for that. Okay, we are going to study that later on, but this actually represent the spin quantum number. All right, so these are the 4 quantum number that you need to know before we move to the main topic of filling of the electron in an electronic configuration. Okay, so let's just do a numerical based on one example based on this. For example, you have 1s. Okay, so in this particular case you have to tell me what is its what is its what are its all 4 quantum number. Okay, so in this case, as you can see, 1 is written, so obviously n is 1, and then s is written. So in this case, the next quantum number, that is azimuthal quantum number, let me just erase this. Yeah, so the azimuthal quantum number in this case would be 0, right? And what about the magnetic quantum number, ml? It will be again 0, right? And what about the ms? That is the spin quantum number. So that will be plus half and minus half. Okay, another little bit complicated question if I have to ask, find all the quantum number for, let's say, 2p5. Okay, so you are being already been given a location. Okay, your electron is present in 2p5. What are the different quantum number, or you can say what is the address of this particular electron. Okay, so how to do that? We can easily see n is 2 in this case. What about l? L is 1. Why? Because for p, l is 1, right? What about ml? So we know that ml is given as -1, 0, +1. Okay, but we don't know exact. We are supposed to tell them exact which ml are we talking about. The electron can present at -1, 0 or +1 anywhere, right? So for that we need to draw this. Okay, so when we start filling the electrons, this 5 represent the 5 electrons. Okay, so first we will fill all the electron with the upward spin. So 3 are already there, then 2 left. Then we will start filling it in the opposite direction spin. 1, 2, and the value for this is -1, this is 0, this is +1. This is represent px, py and pz and so on. Okay, so this is -1, 0 and 1. So here we are talking about 2p5, that is the 5th electron. So you can see 1, 2, 3, 4, 5. This is the 5th electron, right? So we can say in this case ml is basically 0. What about the spin? The spin of the 5th electron is in the opposite direction, right? So in this particular case, ms would be -half. Now you must be wondering that why did we fill the electron like first single the upspin to all the orbitals and then start filling it in the downward direction? Then there is a reason behind it. It all governed by certain rules and the concept or the principles that we are going to study in the next video. So if you don't understand like what actually goes behind this and you just understood a bit part of it like NL, then that's also fine. So just continue watching rest of the videos. The concept will become clear to you. All right. All right, then I'll end this video, and if you have any doubt you can comment down below. All right. Thank you so much. I'll see you in the next video.